One-tailed versus two-tailed hypothesis tests. Let's have a look at an example. Suppose that the bank suspects that the average default losses among its customers might exceed 4%. So the hypothesis is that the mean or the average default loss among all its customer base will exceed 4%. So that's what a hypothesis is. It's a statement about the entire population. In this case, the entire population is represented by the entire customer base for this bank. But the bank is not going to necessarily survey all its customers in order to forecast what the default losses might be in the future. Instead, what they'll do is they'll draw a sample. And based on the findings from the sample, they'll make an inference about the population as a whole. So let's have a look at the sample. The bank drew 70 customers' historic credit records. And they found that the average default loss among these 70 customers was 5.7%. And the standard deviation of the sample was 8.1%. And here's how to interpret the 8.1%. You have 70 observations, but one mean. So naturally, we want to know how dispersed these 70 observations were around the mean itself. So how dispersed were these individual observations? But here's the thing, ladies and gentlemen, we're not interested in the dispersion of individual observations because we're testing for the mean, not individual observations. So rather than looking at standard deviation, we're going to be looking at standard error of the sample mean. In other words, I don't want to know the dispersion of individual observations. I want to know what the dispersion or the error is associated with our estimate for the mean. And how do you find standard error? You simply take standard deviation and divide it by the square root of n. Why do we divide it by the square root of n? Well, you can see as the sample size gets larger, the error or the dispersion associated with the mean decreases. So there it is. So that actually I recommend that you make this conversion at the very beginning of a hypothesis test, because otherwise if you go on to use standard deviation, you'll get the wrong answer. What we want is the standard error of the sample mean. So okay, plugging in these values, 8.1 here, square root of 70 there, we get 0.968, and again this represents the standard error associated with our estimate for the sample mean. Now, let's suppose that the bank sets a level significance of 10%. In other words, what they're saying is the bank wants to give a 90% margin of error to the null statement. So let's stop right there. Where is this coming from? Well, this whole test is based on a sample, and samples have errors. So for example, let's say the bank has 100,000 customers. Based on the group of 70 customers that you pick for your sample, you're going to get different results. So you can see where the error comes from, right? So based on sample selection, you're going to get a different sample mean. So we need to factor in that error, and that's exactly what this does. It says because there's errors associated in this test, we're willing to give the null statement a 90% margin of error. Now, how do we set up the hypothesis? Recall the hypothesis was that the average default loss is expected to exceed 4%. Now there's two ways we can set this up. If you set this hypothesis up as the null, then remember you're giving the null a 90% margin of error. That's a pretty wide goalpost, right? So it's a less stringent test because you have a wide goalpost. So it's very easy for you to come within the goalposts. On the other hand, if you take the hypothesis and set it up as the alternative only has a 10% wide goalpost. So therefore, this becomes a more stringent test. And here's an analogy that I have for you. Suppose that you have two universities. And the first university accepts 90% of all candidates. The second university only accepts 10% of candidates. And if I asked you which is a more stringent university, i.e. which is a more reputable university, well, I think the one that only accepts 10% of all candidates, that must be the tougher university to get into. So that would be a more conclusive indication that we're looking at high quality candidates. And it's the same thing here. If you want stringent test, i.e. you want conclusive evidence, you don't make the test easy by accepting 90%. You make the test hard by only accepting 10% as a confirmation. So what was the point of that analogy? Here's what it all boils down to. If the hypothesis has an inequality, i.e. greater than or less than, as we do here, just make it the alternative and we'll just keep it at that. It's as simple as that. So that is the practice. So now that we've set up the groundwork, we can go ahead and do the hypothesis test. I have the hypothesis steps simplified down to just 4 steps. And here it is. Step 1, we state the hypothesis. Now the hypothesis was that the population average is greater than 4, but since we see an inequality, we make it the alternative. And that's exactly what I did here. I took that hypothesis and I made it the alternative. Therefore, remember the alternative and the null are complements to each other. So if the alternative says the average is greater than 4, the null would say that the average is less than or equal to 4. Step 2 is the level of significance. This will be given, and remember the implication of this. We want to give the null a 90% margin of error. And step 3, we identify the distribution for the sample. And what's the sample here? The sample is the mean. We're testing for the mean. So then we're going to ask, how's the sample mean distributed? Right? Now, when you're looking at distribution of sample means, there's only 2 distributions possible. Z distribution and T distribution. And this was covered in a previous module. And so if the population variance is unknown, which is generally the case, we use the T distribution. On the other hand, if the population variance was known, or if the sample size was really large, then we would use Z. But here it is, ladies and gentlemen. For the exam, for the purposes of the exam, the only way we can use T is if they give us the T table or they give us excerpts from the T table. So the point I'm trying to make here is, it's not going to be left up to your discretion. So you're not going to come across this gray area where you're arguing internally whether you should use a Z or a T. The only way you can use T is if they give us some table values. And then finally, step 4, we do the test. Now, the analogy I use for a hypothesis test is that of penalty kicks. And the way penalty kicks work is as follows. So here we have the middle. And then you set up some goalposts on either side, right? So there's your goalpost. And then it's just a question of where the ball went in. So if the ball comes in here, it's a score. If the ball goes outside the goalposts, then it's not a score. What's that got to do with hypothesis testing? Well, the ball is really the sample. So if the sample falls anywhere within this goalpost, we go ahead with the null. On the other hand, if the ball comes in, or I should say the sample falls outside of that goalpost, then we reject the null. So that's why I use that penalty kick analogy. So let's go ahead and set up the goalposts, and these are referred to as critical values around the null. Now, since the null says mean is less than 4%, we must accept all test results that are less than 4%. So this includes the entire left side of the distribution. So let's come here, right? So here's our distribution, ladies and gentlemen. And so at the center is your null. This whole test is based around the null. Okay. Now, what is the null saying? So go look at the null. The null says less than 4. So what if the sample was negative infinity? So what if the sample was negative infinity? Would that be a confirmation or rejection of the null? Well, negative infinity, let's see here. Negative infinity is less than 4. So that would be a confirmation of the null. So that gives us a clue that the null range starts from negative infinity and goes all the way up to some point on the right side of the distribution. So the 90% covers the entire left side of the curve. So that's the trick I use to determine how to position the body of the distribution and the tail. So naturally, if this is 90%, then the tail is 10%. So that would be the alternative territory. And here's the way to read this test. If the sample falls anywhere in this range, it would be a confirmation of the null. We would go with the null. But if the sample falls anywhere in that range, then it's outside of null range, and therefore we would reject the null. So again, if the sample falls here, we would say, you know what? This is not a margin of error thing. If the sample came way outside acceptable margin of errors, so therefore the sample does not support the null, and therefore we're going to go with the alternative. So the only question is, ladies and gentlemen, where is this goalpost, and where did the sample fall? And there it is. So here it is, sample statistics. So that would be the ball in my penalty kick analogy, and what it measures is how much did the sample deviate from the null. And that's the other thing, ladies and gentlemen, everything is measured from the null. So whether it's the goalpost or whether it's the sample, it's all measured starting from the null. So let's go ahead and calculate these values. So first the goalpost, these are referred as to T critical. And so to find T critical, basically what T critical tells us is how many standard deviations do you need to move away from the null in order to construct your margin of error. So to calculate the T value, the T critical, we need to specify two things: the degrees of freedom, which is n minus 1. In this case, it works out to 70 minus 1, which is 69. And the single tail area, which in this case is 10%. So I'm going to take you to the t-table very quickly, and we're going to look for this degree of freedom and this one-tail probability, and the table will tell us how far we need to deviate away from the null. So here we are with the t-table, and you can see that we have to specify the area for one tail, and at the same time the degree of freedom. So degree of freedom in our case was 69, so the closest number we have is 70, and at the same time the single tail area was 10%, and you can see that's right there. So when we triangulate, so degree of freedom in conjunction with the single tail area, we get a standard error of critical value of 1.294. There it is. So this forms our critical value. And again, what this tells us is how far do we need to deviate from the null in order to construct that acceptance range for the null itself. And so the next step is the t-stat. So this would be the ball in my penalty kick analogy. In other words, did the ball fall within the goalpost or outside of the goalpost? And what t-stat tells us is how far did the sample deviate from the null measured in units of standard error. So when we plug in all these values, we can see that the sample deviated by plus 1.76 standard errors away from the null. So if we go back to our distribution, so here's the null. Now remember, the goalpost is 1.294 standard errors away. So 1.76 would be even further away. But then you look and you say, oh, the sample fell within the alternative territory. So we're going to go with the alternative and therefore reject the null. And there's the decision rule right there. Since the sample, i.e. the ball, came outside the critical values, in other words, the goalpost, we reject the null and therefore accept the alternative at the 10% level of significance. In other words, when you rejected the null, here's what I'm going to, let's have a conversation. You rejected the null. And I'll say, now how do you know you're right? Because you drew a sample and samples have errors. So it's possible you made a mistake. Because we don't know what the true population value is. And here you are rejecting a claim, and you don't even know what the population value is. So that's why this last statement, or that last part, is important. So when you say I rejected the null, you have to tell me how certain you are in that statement. So therefore, I am 90% certain that the null is false. And how do we interpret this? So we are 90% confident that the default losses for the population is now exceeding 4%. And so where is this coming from? Well, when you reject the null, and I made that statement over here, ladies and gentlemen, I made that statement here. When you reject the null, that automatically implies you accept the alternative. So let's go have a look at the alternative. Here it is. And this is why setting up the steps in hypothesis testing is so important, right? Because everything is structured. At the very end of this process, we said we're going to go with the alternative. Well, what is the alternative saying? It's saying that the average, in this case, average default loss is exceeding 4%, which is exactly the conclusion we draw at the end.